Welcome everybody. In this part we will discuss together the aircraft equations of motion. In addition to static stability, the aircraft also must be dynamically stable. An airplane can be considered to be dynamically stable if after being disturbed from its equilibrium flight condition, the resulting motion diminishes with time. To understand how an aircraft behaves, it is essential to develop and understand the aircraft equations of motion. The equation of motion consists of one side of the equations made up of the applied forces and moments, and the other side of the equations providing the aircraft response. The aircraft equations of motion are obtained by applying Newton's second law to a rigid aircraft. Newton's second law states that the summation of the applied forces acting on the aircraft is equal to the time rate of change of linear momentum, and the summation of the applied moments acting on the aircraft is equal to the time rate of change of angular momentum. To develop these equations of motion, it is necessary to understand the various axis systems. The figure shows the body axis system fixed to the aircraft and the inertial axis system that is fixed to the earth. The body axis system is fixed to the aircraft with its origin at the aircraft center of gravity. The x-axis is defined out the nose of the aircraft along some reference line. The reference line may be chosen to be the chord line of the aircraft or may be along the floor of the aircraft, as is often the case in large transports. The y-axis, the y-body axis, is defined out the right wing of the aircraft, and the z-axis is defined as down through the bottom of the aircraft in accordance with the right-hand rule. It is relatively easy to determine the moments and products of inertia in the body axis system because it is fixed to the body of the aircraft. On the other hand, the earth axis system is fixed to the earth, with its z-axis pointing to the center of the earth. Often, the x-axis is defined as north, and the y-axis is defined as east. The earth axis system is assumed to be an inertial axis system for the aircraft problems. The word inertial in this context means fixed. This is important because Newton's second law is valid only in an inertial system, in a fixed system. While this assumption is not totally accurate, it works well for aircraft problems where the aircraft rotation rates are large compared to the rotation rate of the Earth. Now, we will derive the rigid body equations of motion through the conservation of linear momentum, then the conservation of angular momentum, starting with the conservation of linear momentum first. As agreed before, the rigid body equations of motion are obtained from Newton's second law, which states that the summation of all external forces acting on a body is equal to the time rate of change of the linear momentum of that body. Consider the airplane shown in this figure. If we let the infinitesimal mass dm be an element of mass of the airplane, and the velocity v be the velocity of the elemental mass relative to an inertial frame, and the infinitesimal f delta f be the resulting force acting on the elemental mass, then the Newton's second law yields that delta F equal delta M times dV by dt. The velocity of the differential mass dm is V equal the velocity of the center Vc plus the relative velocity dr by dt. So Vc is the velocity of the center of mass of the airplane, and dr by dt is the velocity of the element relative to the center of the mass, dr by dt. And the total external force acting on the airplane is found by summing all the elements of the airplane. So the summation of the infinitesimal delta F equal the total forces applied to the airplane F. Substituting in Newton's second law with these two relations, V and the summation of delta F, we get the following: that the summation of delta F, which is equal F, equal d by dt, summation of Vc plus dr by dt times delta M. Since Vc is the same for all elemental masses, and assuming a constant mass, we get F equal M, this is the summation of delta M, times dvc by dt, d by dt operated on Vc, so dvc by dt, plus d by dt dr by dt times delta M. And we can pull the differentiation sign out of the summation sign to get. So we have pulled d by dt with that one. So we get F equal, the first term is the same, m dvc by dt. The second term become d square by dt square for the summation of r delta m. If we remember, this is the definition of the center of the gravity, center of mass of the airplane. So the summation of r delta m is equal to 0. The fourth equation then becomes F equal m dvc by dt, which relates the external force on the airplane to the motion of the vehicle's center of mass. The problem now is that the vector Vc, this vector, is referred to the body axis system, which is a rotating system. Let's recall some vector differentiation basics. It can be shown that the derivative of an arbitrary vector A refers to a rotating body frame having an angular velocity omega can be represented by the following vector identity. The derivative of an arbitrary vector A with respect to an inertial frame I is equal to dA by dt with respect to the body axis, which is another rotating frame, plus omega. Omega, this is the angular velocity vector of the body axis cross A. So for any vector, if you want to differentiate it with respect to inertial frame, which is the case in the Newton's second law, all the derivatives with respect to time should be with respect to inertial frame. So you have to differentiate it first with respect to the body axis plus omega. Omega is the angular velocity vector of the body axis cross the vector A. Applying this identity to the equations derived earlier yields, which was F equal the mass of the airplane times dvc, the velocity of the center of gravity of the airplane, dvc by dt. Applying this identity to this equation, we get F equal m. First, we have to differentiate this vector vc with respect to the body rotating axis or rotating body axis, dvc by dt, then adding omega cross this vector vc, and m is multiplied in both sides. The omega vector equal p in the direction of I plus q in the direction of j plus r in the direction of k. So this is the roll motion around the x-axis. This is the yaw motion around the y-axis, and this is a pitching moment around the y-axis, and this is the yaw motion around the z-axis. So this is the components of the angular velocity vector of the airplane. And Vc equal u in the direction of I, v in the direction of j, w in the direction of k. So this is the linear velocity vector with respect to the body axis. So this is the angular velocity vector with respect to the body axis, and this is the linear velocity vector with respect to the body axis. And dvc by dt equal u dot I plus v dot j plus w dot k, and this is the linear acceleration vector with respect to the body axis. The force components are composed of contributions due to the aerodynamic, propulsive, and gravitational forces acting on the airplane. Fxi plus Fyj plus Fzk. These are the components of the force along the x body, y body, and z body axes respectively. Equating I, j, and k coefficients from both right-hand side and left-hand side of this equation, we get the following three equations of fx equal m times this bracket, fy equal m times this bracket, fz equal m times this bracket. Notice that the dimension of each of these terms is acceleration dimensions. This is u dot, so this is its units is acceleration, q, which is angular velocity, radian per second, times meter per second, w, this is the vertical component or the z body component of the linear velocity, meter per second, time radian per second. So the total unit will be meter per second square, which is acceleration. So acceleration time moment, time mass is a force unit, mass time accelerations. So this is three equations of motions coming from the conservation of linear momentum. This is a system of nonlinear differential equations in the unknown variables u, v, and w, which are the body axis components of the linear velocity vector. The known terms of these equations, which are the inputs to the system, are the forces Fx, Fy, Fz, which are on the left-hand side of these equations. The solution of this system of equations also requires the knowledge of P, Q, and R. The variables B, Q, and R will be the outputs of the conservation of the angular momentum equations, which will be discussed next. The second part of Newton's second law is the conservation of angular momentum. Newton's second law states that the summation of the external moments acting on the body is equal to the time rate of change of the angular momentum, which is the moment of momentum. For the differential elements of mass delta m, the moment equation can be written as infinitesimal moment equal rate of change d by dt, the infinitesimal angular momentum, which is the moment of momentum r cross mv. But because m is a scalar quantity and v is a vectorial quantity, so it is written like that: d by dt r cross v, all times the infinitesimal mass. Again, v is equal to vc, the velocity of the center of gravity, plus the relative velocity, which is dr by dt. dr by dt. And the derivative dr by dt should be with respect to inertial frame. So it will be equal dr by dt with respect to a body axis plus omega, which is the angular velocity vector, times r. But since we assume a rigid body frame, so dr by dt with respect to body axis is equal to 0. So finally we get v equal vc plus omega cos r. So this v equal vc plus omega cos r. The total moment of momentum can be written as follows: h equals the summation of the infinitesimal angular momentum, which is equal to the summation of r cos vc times delta m plus the summation of r cos omega cos r times dm. This is by substitution in this equation. So this v is equal vc plus omega cos r, and r cross v, so r is crossed by vc and r is crossed by omega cross r, and delta m is multiplied by both expressions, delta m and delta m. The velocity Vc is a constant with respect to the summation and can be taken outside the summation sign. Taking into consideration the order of cross multiplication, we get, so this Vc now is out of this summation, so we cancel these brackets. So by the definition of the center of gravity, we know that the summation of r times dm or delta m is equal to 0, though, so the whole term will be cancelled, and the angular velocity vector now can be expanded into p I plus q j plus r k, and the position vector can be expanded as xi plus yj plus zk with relative to the body axis. Substituting and expanding the angular momentum equation and equating I, j, and k coefficients from both sides, we get the scalar components of the angular momentum to be as follows. So by substituting these angular velocities and the components of the position vector r into the h equation, take care that h is the angular momentum, and Newton's second law is talking about the rate of change of angular momentum. So now we are preparing h, which is the angular momentum. So the x component of h is this equation, the y component is this equation, and the z component is this equation. The summations in these equations, all these summations, are the mass, moment, and products of inertia of the airplane. The final angular momentum components are as follows: hx, hy, hz. Since this is the definition of Ix, this is the moment of inertia around the x-axis, the x-body axis, and this is the moment of inertia about the y-axis. This is Iy, the definition of Iy. This is the definition of Iz. This is the definition of Ixz, and so on. So we get the final relations, which are the components of the angular momentum in the three directions x, y, z with respect to the body axis. If the reference frame is not rotating with the airplane, then as the airplane rotates, the moments and products of inertia will vary with time. To avoid this difficulty, we will fix the axis system to the aircraft, which is the body axis system. Back to Newton's second law. Now we must determine the derivative of the vector h, the angular momentum, which is referred to the rotating body frame of reference to a fixed inertial frame. Recalling that if you have any arbitrary vector A and you want to differentiate it with respect to inertial frame, you have to differentiate it first with respect to the rotating body frame, then adding the omega vector, which is the angular velocity vector, plus the vector itself. So applying this formula to the Newton's second law, So we have to differentiate first the angular velocity with respect to the body axis frame, then adding omega plus the vector itself, which is the angular velocity with respect to the body frame. After expanding the omega vector and the h vector from this expression, because we have three components of h, hx and hy and hz, which were uh, derived previously in the last slide. So after expanding this omega and this h and equating the I and j and k coefficients from left hand side to the right hand side of this equation, we get the following expressions. L is the moment in the x direction, m is the moment around y, n is the moment around z. This is the three components of the total moment vector applied to the airplane, equating them to the corresponding I, j, and k components from the right hand side. So we get these expressions. A very famous assumption is to assume that the xz plane is a plane of symmetry of the airplane, and this is almost true for most airplanes. Hence, Iyz equal Ixy equal 0 for this assumption. The moment equations will be simplified to the following. The output of the conservation of angular momentum equations will be B, Q, and R, which are the body axis components of the angular velocity vector. The inputs to the conservation of angular momentum equations are the body axis components of the aerodynamic and the thrust moments acting on the aircraft, which are L, M, and N. So giving this input to the system, L, M, and N, if you can solve these nonlinear differential equations, you can get R, B, Q, which are the angular velocities around the body axis. The derivations of the previous three conservation of linear momentum equations and the three of conservation of angular momentum equations are conceptually separated. However, recall that P, Q, and R are also required for the solution of the previous conservation of linear momentum equations. Therefore, given this coupling, the conservation of linear momentum equations and the conservation of angular momentum equations must be considered as a single system of equations. Note that Fx, Fy, and Fz are the components of the force along the x-body, y-body, and z-body axes. Note also that the force components are composed of contributions due to aerodynamic, propulsive, which is thrust, and gravitational forces acting on the airplane. But the weight vector, this one, of the aircraft is conveniently represented in the Earth axis system, where there is only a component in the positive z direction because the vector acts towards the center of the Earth. So we have only one component, mg, in the positive z axis. This is the z of the inertial frame. This is the inertial frame. So usually we represent the gravitational force in the inertial frame, not in the body axis frame. While the derived 6 equations of motion are conveniently displayed in the body axis, then gravity vector must be transformed into the same axis system before it can be added to the equations of motion. As a result, it is very important to understand how to transform a vector from one axis system to another.